Okay, welcome back after the break. Now we finished our lectures for today and we'll continue in a more informal setting with the first tutorial or exercise session, as it is called. So you're all very, very welcome to ask all your questions and don't just listen attentively, but also think for yourself, try to do the calculations, and yeah, let's learn as much as possible.
Okay, so welcome back. Thank you for coming back. You could have escaped. The way I want to do this is, I think I'll take questions first, and then there are throughout these notes some exercises. We have not actually gotten too far yet. There's only there's one that I'm going to present to you on the board, and one that's in here. As we get later on, there'll be more, and the exercise density begins to grow both in difficulty and in density. So there'll be many more for us to do later. But for now, there's not too many yet. So I think maybe I'll just take questions first, and then I'll try to steer the discussion towards an exercise. And then if I fail at that, I'll just say, okay, now we're going to do an exercise, and then we'll do it. And I think it's best if people try them themselves, and I'll walk around and provide assistance, and then I'll do some stuff on the board and so on. But first, questions. Anyone have any questions? On anything? No. Yes, thank you.
I was wondering
about
basically how to translate these pictures when you're moving defects around in space into equations, basically. Oh, sorry.
So the question for the recording was, you're wondering how to translate these things from sort of pictures in space to actual equations. So the truth is, these are each of these things that I write down. Let me give you an example of a terrible, weird, equation in space. I think you mean things like this, maybe, like I wrote down Q of S2 O of X equals to I O of X. Is this what you mean as an example of something? Yeah. So the truth is, you can really view this as an equation that holds within the path integral. Okay. What this is saying is that if you compute in the path integral, for example, this expectation value, which is a very well-defined thing to do in the path integral, then it will be equal to always this expectation value. Okay. In fact, it will be true for not just this expectation value, but rather you can even insert any other operators that you want in here. Okay. And it will be true provided you do it so that those things are not interfering with the collapsing process of my S2. So you can insert other operators, O of Y, O of Z, blah, 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 anywhere else, so long as they don't interfere with the collapsing process of this S2, then this equation will still hold. If you do insert them there, then there's a modified equation that is not exactly this. You have to add extra terms from that. But this really is an equation you should view as the way we always view like operator equations in a path integral, they always sort of hold as long as nothing else gets in the way, right? That's sort of what you imagine when you write an operator equation in the path integral. This is on the same footing as that.
Okay, yeah.
Does that answer the question? Yeah.
Yeah.
So I think that there is a related question, which maybe we'll get to a little bit later, which is, having said all that, when you learn quantum field theory, you learn it differently, right? This is the definition of a symmetry generator, right? So these two things are actually equivalent, okay? So in fact, maybe we can even get into this. My first exercise that I had here was the following. Prove that this, in the path integral, without the expectation values. So this is if you have the notes, this is on page 10 of the notes. Prove that this fancy higher form symmetry, blah, 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 whatever thing, is equivalent to this operator statement. This is an operator statement. These are all operators on the Hilbert space. Prove that this is equal to this by cutting open the path integral. Okay, this is my first exercise. So in fact, let me maybe, people take a second and talk to your neighbors and try to prove this. It's a lot less, it's not actually much work. It's just, you have to understand what these things mean, when you think about this. I'll mention that in Nella's lectures, she went back and forth a few times, right? From path integral to Hilbert space, path integral to Hilbert space. So this is a completely doable thing. So yeah, so why don't people think about this a little bit and try to understand what this means? Yeah.
So it's probably not S2, but S some other number.
Sorry?
In this Q, it's not S2, it's S3-1.
Sorry, my bad. Yeah. I've been in 3D too long. Yes. Did I write S2 in here? No, yeah. SD minus 1. Yeah, that's important. Yeah, thank you. I can only visualize R3, to be completely honest, so I keep writing S2 everywhere. Yeah. Yeah. So everyone give this a try. Yeah. Yeah. Yeah.
Write down this function. It's going to have QO minus O.
Yeah.
QO something like this.
Yeah.
O Q something like this.
Yes, that is exactly the right picture. Yeah, that's basically it. Yeah, that's basically it. Yeah. Okay. So we'll let other people think about it a little bit, and then I'll draw the picture for that on the board. But that's exactly it. Yeah. Okay. So a few people I think have gotten it. I might just walk around a bit and just yeah. If you want inspiration, raise your hand and you know. Yeah. Yeah. Yes, inspiration. Okay. Yeah. So yeah. So the key thing here is the ordering. You see, the commutator involves an ordering, right? And so you have to somehow get the ordering from the path integral. Now, where does ordering come from in path integrals? It comes from the time ordering, right? In other words, there's a time direction, and the things in the path integral that are in a particular time order give you, you know, that gives you the ordering in the Hilbert space picture. So you have to somehow understand that there's an ordering that's present in this SD minus 1, which is the right ordering to get the commutator. That's basically the idea. That makes sense. So now draw a bunch of spheres now. You should be taking spheres and squashing them. You know, that's what you should be drawing. Yeah. So yeah. Okay. All right. It's become eerily quiet. Does that mean everyone has proven it yet? Does anybody want inspiration? Yeah. Yeah. Okay. Okay, so okay, let me now do it on the board. I think most people have thought about it a little bit. So what is the idea here? You see, there's a key thing about the way sort of commutators work with how sort of operator ordering is inherited in the path integral, right? There's this basic fact that when you do a path integral, so say it doesn't matter what you pick, it turns out, but say you call that time, right? Then the operator ordering in the quantum theory that is inherited from the path integral is always time ordering. Right? Is everyone familiar with this from your, I mean, the rough idea is just that you can always cut open the path integral, and that means that the ordering that has to happen is always consistent, so it must always be consistent with picking a fixed ordering. That explanation makes no sense if you don't already know what I'm talking about, but hopefully that reminds you of what, from your memories of what I'm talking about. Okay, so let us think about what this picture says about operator ordering and check if it agrees with this or not, okay? So this is going to be more of this drawing pictures thing, but it's hopefully fine. There's always, maybe a thing to point out is that for every picture, there's always an equation that you can write down, which involves something like this, okay? So first I'm going to start with this. So the left-hand side of this is the following. You take your charge defect operator and you integrate it on a sphere, and you have some operator O of x in the middle. Okay, the sphere wraps it, and this is a thing in the path integral. Okay, so now I can imagine squashing this, right? By squashing it, what I'm doing is I'm sort of inflating it in this direction and sort of squashing it in this direction. Okay, so in other words, this is topologically equivalent to the following thing. It's like a giant pancake. You see what I did? I took it and it's still topologically a sphere. Okay, so it's still the same thing because it's a topological defect, but it's squashed. Okay, and now there's the edges of this, right? Let me take those all the way out to infinity. Okay, so far out that maybe I just basically don't really see them anymore. Okay, so now it looks like this. Okay, all right. Okay, now what is this picture happening here? So notice that I'm going to call the top one Q1 and the bottom one Q2. Okay, this is basically the sum of Q1. So Q1 is evaluated now on a time slice, which I'm going to call RD plus 1 plus, and this is RD plus 1 minus. Okay? So in the path integral, now there are two terms. Okay? One of them comes from the top one, okay, which is Q1 RD minus 1 plus times O of x. Okay? And one comes from the bottom one, which is minus Q2 R D minus 1, which is a minus. I guess I didn't need this much notation, to be honest. They're just both Q. I should say, this is a good time to say I didn't prepare solutions to the exercises. I'm sort of going to be freestyling them always, and hopefully it works out. Okay, so this is an equation in the path integral. Okay, it's not a Hilbert space equation. It's an equation in the path integral of two surface operators. The minus sign comes from the fact that this is oriented. This is an oriented surface. Okay, and the orientation is therefore different here and there. Okay, that's important. The orientation tells you which way you are doing the charge rotation. Okay, there's information there, and that's why there's a minus here. Okay, so far all I've said is that this is equal to Q of S D minus 1 O of x. These are the same thing, provided nothing bad is happening at infinity. Okay, which we're going to assume. Okay. And now what we want to do is go from this to a Hilbert space picture. Okay? If you realize these as operators in a quantum Hilbert space, again, the ordering comes from the time ordering. And note that here versus here, the time ordering is backwards, right? Over here, Q is on top of the operator O. And over here, Q is on bottom of the operator O. So therefore, once these become operators in the quantum Hilbert space, this becomes QO of x, where this Q is literally just the same integral of J0, the operator, minus O of x Q hat. Okay? I don't know why I put the square brackets. And this, the right-hand side of that was always the same thing. It was always just this. Okay? So does that make sense to everyone? This going back and forth from the path integral to the, yeah.
Can you repeat the last argument, how the orientation of the surface is equal to the time?
It's not the orientation, that's this minus sign. The minus sign is from the orientation. The time ordering comes from the fact, maybe this is what you meant. Let me draw a picture of what's above what. If you look at this from the side, okay, then the time ordering of this with this is the opposite of the time ordering of this with this, which means in the Hilbert space point of view, the ordering of the operators will be different. Okay? And that's the basic thing about going from path integrals to the quantum theory. Okay? So there's, to be honest, now I'm going to become philosophical, there is something quite beautiful about the fact that this sort of very geometric SD is the same as this commutator. You know, it's really quite nice. When you first learn about path integrals, you're like, oh, this time ordering thing is some trick, you know. But it's really very important because it makes possible this geometric realization. And many other beautiful things happen. It's not a trick. It's not a bug. It's a feature of the path integral, that the time ordering is like that. Okay. Yeah. Yes.
So the first thing that bothered me a little bit is that you said it's a topological invariant in some sense.
Yeah.
Two planes are non-compact and disconnected.
Yeah.
Here is compact and connected.
Yeah. So I'm now exposing my lack of mathiness. So in a fancy way, what you could say is that the plane, together with the point of infinity, is topologically the same as a sphere, right? And what I'm really saying is that nothing is happening at the point at infinity. So I can add or subtract it however I like. That's, I think, the fancy way to say it. The more physicsy way to say it, I think, is just that these things go off to infinity. I'm going to assume nothing leaks out, basically. And therefore, if nothing is leaking out, I can take these two things and glue them together like that. What's really important is, when I say topological, I really mean it's kind of in a loose sense. Like, I just mean, if I can take this and deform it, I mean topological to the extent that I don't hit anything else. It's topological as long as I don't hit anything. So in this case, as long as there's like no flux tube poking in from infinity, it will be topological. And in some cases there might be, and then you really need to think about it hard. So there'll be, despite the fact that I'll keep saying the word topological over and over and over again, there'll be very little formal, like, actual math topology in these lectures. Topological really means invariant under small deformations. That's the sense in which I'll use the word topological. Okay. Good. Excellent question. Yeah. Yeah.
Second question is on how do you go with the vertical line? Because you have the cubes the other way around, downstairs and upstairs. So
Yes, absolutely. So this comes from the time ordering. So first of all, I should point out there is no information in the ordering here. This is an expression in a path integral. And there's no ordering, there's just no ordering. In a path integral, everything is Euclidean time. You can put them, it doesn't even mean anything. Like, what I mean is, this is a path integral expression, which means that you integrate over all your fields, and you should view Q as a functional of phi, and O as some other functional of phi. And in the path integral, these are just numbers, right? You can put them however you like. It doesn't mean anything. It's when you go to the Hilbert space picture that this means something. And in general, when one goes from a path integral to a Hilbert space, the ordering comes from time ordering always. Okay, that's how the Hilbert space picks what ordering to put the things at. So this is not some fancy thing about the higher form symmetries or anything. It is just normal quantum mechanics in a path integral. If you're doing a path integral, as Nella was doing, of two operators, Q of T1, Q of T2, then in the Hilbert space point of view, this is theta, T1 minus T2, Q of T1, Q of T2, plus the other way around, T2 minus T1, Q of T2, Q of T1. There's formulas like this that appear in sort of basic path integral textbooks. These are what I'm using to go from here to here. Okay. Okay. Excellent. Good. Other questions? Yeah. So how are we doing? Really well, actually. Okay, good. So I had another question from here, which was the following. So now I sort of want you to go the other way. This is going to be really easy for all of you, but let's do it anyway. Now I sort of want to go the other way. Is there even any point in doing this? Yeah, why not? Okay. So okay. So I wrote down the following thing for a non-abelian group, OB. So let me just remind everyone, this is for a non-abelian group. This is the operator who generates a finite phase rotation. Now what I want you to do is let's see. So I feel like this is too easy. I think it's going to be a one-liner for everyone after this long discussion. Let's ignore it and move on to a different, more interesting problem. Okay. So yeah, I think I explained the last one in a bit too much detail. Yeah, question. Yeah.
Sorry.
Yeah.
Mm-hmm. The entire concept.
Yeah.
I'm wondering, you have this topological operator.
Yeah.
You have this topological operator.
Yeah.
For instance, depending on the sphere, and we can act with this on our field on X if X is inside.
Yeah,
but if this X is not inside or our field is somewhere else, we can contract it to just a point. Nothing is going to happen. So this topological operator really just makes sense depending on which fields it acts on. So it's not. Okay.
I think that's pretty much correct. Yeah, I would agree with that. Yeah.
Okay, so it's okay. Yeah, it just sorry.
No.
So it's kind of the representation is already like included in this topological operator.
Sorry, what was the last thing?
Is the representation then already included in this in this operator.
The representation of the symmetry algebra, you mean? No, it's not really included there. This is the same as in normal. Let's just remember how this works for normal, normal without this fancy representation, without this fancy topological stuff, and then go back. So if you recall, if you have a normal, say you have a non-abelian symmetry, so you have something like QA, do this labels like say the Lie algebra of some non-abelian symmetry, and say it acts on some operator OI, then the way in which this works, I think, is something like you get something like Vij. Sorry, this is the I want the infinitesimal one, which is not the same notation. It's something like Tij AOJ, right? There's some formula like this where you act with a infinitesimal rotation. Now, would you say that the information of the representation is stored in the Q operator or in O? I would say it's stored in O because O, carries that, O is what, Q is the same for all, well, maybe it's a bit subjective actually. Q is the same, but it's true, it includes the sum over all your degrees of freedom, and it will probably include that thing. Maybe it's a bit subjective, but this is what happens for normal things, and it's exactly the same for this. Yeah, is the information of the representation? I don't know, something, I think you're right. I think one could, if you actually have a Lagrangian description of this thing, then actually it is true that within Q, there's going to be a term that involves, that. In that sense, the information is stored within Q in a Lagrangian description. If you don't do a Lagrangian description, it's a bit more confusing. Like if you're doing ADS CFT, for example, then there's no useful sense, I think, in which it's stored there, but now we're getting a bit there. So I agree with you, yes. Yeah. So yeah. Sorry, for everyone, that was a quasi-philosophical discussion maybe, but yeah, this is what happens in normal field theory, and it's the same for this one.
Okay.
Yeah. Yeah. Other questions? Sorry, did I answer your question or?
Yes. I was just confused that it depends, so that this, depending on which surface we take, the result is completely different. But if I hit, even if I hit the same field.
Yeah.
Okay.
That's right. Well, it's the same field. I would say it's like this, right? If you hit different fields, you get different answers here. That's what you're saying, right? Yeah. This is the same. This is a shocking fact about commutators in quantum field theory, and it's the same thing about these things collapsing on points. Yeah.
Okay. Nice. Thank you.
Yep. Good. Yeah. Other questions? Other questions about this? Okay. This is just a question. Is everyone happy with wiggling these topological operators around? We're going to do much more crazy things with them soon. So I want everyone to be happy with them in this setting. Where at this point, I have done nothing that you have not already seen in ordinary quantum field theory lectures. I've just written them in, in like a fancy and more abstract language. Everyone is completely happy with this, right? Okay. Okay, good. All right. So then I have another suggested question, which I didn't put into the thing, but I realized that I probably should have. I didn't know where to put it, so it would be too early. So I made a statement about two theories being equivalent earlier, the compact free boson and the compact scalar in 3D and the gauge field in 3D. I was thinking it would be good to prove this and to understand how the global symmetries map. Does that sound reasonable to people? Okay, let's do this. So here's a claim. I think what I'm going to do is I'm going to go, which way is more fun? I'm going to go from the scalar to the gauge field, okay? So this is a theory, d mu theta squared, okay? Now, this theory has actually two symmetries, okay? One of them is of a higher form type, so I sort of technically shouldn't talk about it till tomorrow. So I'll leave that one out. But this is a sort of obvious symmetry, right? This one, delta theta equals to constant. So rather, let me write it this way. Rather, theta goes to theta plus constant. Okay? This is a symmetry of that Lagrangian. Okay? What is the Noether current of this symmetry? You can figure this out. Current of the symmetry turns out to be just d mu theta. Okay. The way to prove this is just through normal Noether currentology. So let me not do that. But just to make sure everything makes sense, the equation of motion of this is just grad square of theta equals to 0, right? And so therefore, at least it is true that notice that the equation of motion is equivalent to this thing being conserved. Okay. Okay. Now, okay, good. So now the claim is that this is actually equivalent to a gauge theory. Okay. So what I want to do is actually, okay, I'm taking a risk doing this in real time, but I think I can manage. What I want to do is do the duality for you, show you how to do this duality, and I want to do it in a somewhat, let's see, is this going to work? I'll do it first in a way that I'm sure I can do it, and then I'll try to do it in the way that I'm not sure I can do it, and then make sure that works. So I'll start with this, okay? And now I want to do the duality and show you this is equivalent to a gauge symmetry, okay? So how do we do this? So basically, this thing has a basic degree of freedom, which is theta, all right? Now, there is a temptation, because only the gradient of theta appears in this, there's a temptation to take as the fundamental variable not theta, but rather the gradient of theta, okay? Let's take a second and try that, okay? So let me write v mu equals to d mu theta, okay? And now what is my action? My action then is d3x of v squared, okay? All right, and what would the equation of motion be with respect to v? The equation of motion would be v mu equals to 0. Which is therefore wrong, okay? This did not work, this failed. And this is pretty obvious, right? This is a stupid thing to do. The degree of freedom is theta and not v. I cannot do this, okay? Even though only v appears in the action, that doesn't mean that the degree of freedom can be v, because you see, the set of fields that you integrate over here is different, right? In particular, if you have gradient of theta, then certain field configurations will never happen. So for example, this is always 0, right, for any field configuration theta, because of the antisymmetry of the partials. On the other hand, this is not 0, right, generically for any field configuration v. In other words, if I want to make v my basic degree of freedom, I'm counting field configurations that should not exist, right, from this point of view. Okay, so whenever this happens in physics, we know what to do. We just add a Lagrange multiplier to kill whatever it is that we don't like, okay? Let me try to get the indices right. I shouldn't teach people bad practice. Okay. Okay, so now here is a something, right? This is a new theory. This has 2 degrees of freedom in it, not just 1. It has S is a function of V and a function of A, all right? Okay, and now what I'm going to do next is I'm going to get rid of V. By which, because v appears only quadratically in the action, I can simply eliminate it in the action by setting it equal to its equations, by imposing its equations of motion. Okay. So what are the equations of motion? They are v nu equals to a half a nu epsilon mu nu rho. Oh, sorry. I messed that up badly. Should really have prepared for this thing. First, I'm going to take this and integrate by parts. Okay, so that the d nu appears here, all right, and there may or may not be a minus sign depending on the epsilon. Let's just pretend there's a minus sign. And then, and now I'm going to eliminate v nu correctly. The equation of motion from varying with respect to v nu is 2 v nu equals 2 epsilon mu nu rho d nu a rho. At this point, the signs have ceased to be correct, and maybe the factors too, so this is all schematic, but you get the idea. All right? And so now, let me take this and plug this back in here. Okay? You get 2 terms that really have the same structure, right? Each of these terms is basically d nu a rho with an epsilon in it squared. Okay? When you have 2 epsilons that are contracted, they basically become a product of Kronecker deltas, right? So what one gets at the end of the day is that this thing is d3x times d nu a nu d mu a nu. Okay? There's a number here which I'm not calculating. It's like 2 or half or something like that. Yeah.
So I was just going to say,
yeah.
Could you also do this by, in a sense, integrating out that field by computing the square? And then, so if you compute the square, you basically get the partial function saying one of it is a Gaussian integral.
Yeah, yeah.
And you immediately see the remnant just has to be the
yeah. Absolutely, just to repeat the question for the recording. The question was, can you do this by completing the square instead of the somewhat ad hoc thing that I did? The answer is yes, and to be honest, what you should really be doing is, you should be doing this all inside a path integral. And then you have to do it like that. And there's some determinants and so on that you have to show don't do anything. I'm doing this in a somewhat sketchy way. Like the operation of doing this and setting it equal is a little bit, it's correct if it's quadratic, but it's correct if it's quadratic because you can imagine doing it inside of a path integral where it becomes what you just said. So yeah, that would be the more correct way to do it, absolutely. But it's the same idea though in the end of the day. Okay, and so we end up with this thing, okay? Okay, there's a number here, you just want to check this number is not 0, it's not 0, it's something, yeah, okay. Okay, good. All right, what have we done? We have shown that in a theory whose dynamical variable was theta, we can start with a theory with a single scalar dynamical variable and end up with a theory with a single vector field A as its dynamical variable. Okay? Furthermore, this theory has a gauge symmetry. A mu goes to A mu plus d mu lambda, right? Okay. So I actually assigned this problem as a, when I teach path integral QFT, I actually assigned this as a problem. And then at the end of the problem, I write part C. Explain where the gauge symmetry came from in the original Lagrangian. And the truth is, I do this purely for entertainment. This is a horrible thing to do because this is not a question that has an answer, you see. It's very entertaining to read the answers, but it's really just to make you think. So I can ask you, where did the gauge symmetry come from? How do you see the gauge symmetry in this original Lagrangian? And the answer is, there is no way to see the gauge symmetry, okay? There is no gauge symmetry in this Lagrangian, just a fact, all right? There is a gauge symmetry here, okay? So the real lesson from this kind of thing is always, I think, the following thing. You see, gauge symmetry is terribly named, okay? Gauge symmetry is not a symmetry. Gauge symmetry is a redundancy. Okay? It's not a symmetry. If it was a symmetry, then you can see it on either side of the duality. Okay? Symmetries must exist no matter how you talk about the system. Gauge symmetry is not a symmetry, it's a redundancy, it's a description, it's a choice of how to talk about a system. Okay? Okay. Now, I did mention, on the other hand, that global symmetries you actually can see on both sides of the duality. Okay? So one thing you can ask is, what happened to this global symmetry? Okay? Where is it on the other side? Okay? Okay, anyone? Where is the global symmetry on the other side? Any thoughts? What is the global symmetry current? Don't overthink it. So the answer is sort of buried in these formulas, to be honest. Remember the global symmetry current was d mu theta? Yeah, and remember d mu theta was basically V, you know, I mean, it sort of lost its identity somewhere along the way, but it's basically V. So if you trace this thing back, what you can see is that J mu in the photon language, sorry, yeah, Nabil was there. Yeah. Yes, excellent. Epsilon mu nu, and then, what did you say? Yeah, I think you said, yeah. Yeah, okay, I think I've started writing it already. This is the global symmetry current on the other side. Okay? And this is good, right? The divergence of this is indeed 0, right? By antisymmetry acting on this thing. Okay? So on this side we have d mu j mu equals to 0. On that side also we had d mu j mu equals to 0. Okay? So the global symmetry does exist on both sides. Okay, but nevertheless something did happen, right? The character of the symmetry appears somewhat different on this side than on that side, right? In this formulation, when was d mu j mu equal to 0? d mu j mu equals to 0 only when we were on shell, right? I had to impose the equations of motion to get d mu j mu to vanish, right? Over here, on the other hand, d mu j mu is always 0 for any field configuration of A, okay? This is what people sometimes call a topological current for that reason, okay? Now, I'm not going to use this word because the word topological is already overloaded in these lectures, but basically in literature, topological current is one whose conservation happens even off-shell, okay? In a sense, there's very little going into the conservation of this current. It's just there because A exists, okay? Okay, so I really like this example because it honestly shows you a lot of sort of very interesting physics that's going on. So let me ask you another question. This theory has a massless photon, okay? Why is the photon massless in this theory? Anyone?
No A squared.
There's no A squared term, but I don't know. That's true, but like let's put this. Let me try to see this clearly. So, an A squared term could not exist because there is a gauge redundancy in this theory. There is a gauge symmetry, and it is forbidden by the gauge symmetry. Okay. However, I can write down other theories that have the gauge symmetry that will be massive, that have a massive photon, right? So for example, one thing I could do is take this theory and couple it sort of to a complex scalar phi, then condense the complex scalar phi and Higgs out this thing, and then it would end up being massive, right? So that alone is not a good answer. There's more that one can say. Of course, why questions are always a bit fluffy, but yeah. Look at something more. Why is it that this photon is massless? I'm looking for an answer in terms of the global symmetries.
The first one is massless because of the global symmetry that shifts.
Very good. Okay, good. This line is massless because global symmetry that shifts, right? Okay. So what does that mean exactly? Because there's a global symmetry who shifts, that's realized in this way, that means that the symmetry here is spontaneously broken. Does everyone understand that? That's happening? This is actually a theory I wrote down earlier for the sort of effective Goldstone mode action, okay? In other words, this theory is a spontaneously, in this theory, the U1 global symmetry is spontaneously broken, okay? Now, what that means is, in this theory, because it is the same theory in the same phase, the U1 global symmetry is spontaneously broken, right? Okay. A mu is therefore massless because by Goldstone's theorem there must be a massless degree of freedom, and we only have A. So A is, in a sense, the Goldstone mode for that spontaneously broken symmetry. Okay, that's actually why it's massless. Does that make sense to everyone? You know. So note that we have a nice. And if someone ever asked you, no one will ever ask you, but if someone ever asked you why in 3D is the photon massless in massless, in free E&M in 3D, that's why. Because it's the Goldstone mode of this spontaneously broken symmetry. Okay. Good. Let's see. Any other questions about this? What just happened here? Yeah.
I don't quite follow the argument why the left-hand side is spontaneously broken.
Yeah. Good. So there are various ways to see this. So one way is just to note that previously I wrote down an action for the moving around the bottom of this thing. It was the same action, right? And that was a spontaneously broken phase. That's one way to see it. The truth is that's a bit of a cop-out. Okay. The right way to see it is to look for this off-diagonal long-range order that I told you about. In other words, you should compute the two-point function. Jesus. You should compute the two-point function O dagger x, O of 0, okay, as x goes to infinity, and ask what does it do? If it goes to 0, then the symmetry is unbroken, whereas, remember, if it goes to a constant, then the symmetry is spontaneously broken. Okay, these are the two things. Okay, we should do that in this theory, so let's do that, okay? So first of all, what is the operator O who transforms as a phase under the symmetry? The point of O is that under the symmetry, it must transform like this. okay? Which means O is not theta, because theta does not transform like this. Theta realizes the symmetry non-linearly. O is e to the I theta. Okay. So therefore, I want to calculate this two-point function. Okay. Okay, let's do it. This is a Gaussian theory, which means there's some sort of formula that I keep forgetting that means that you can take the exponential of these two things and write it like this. This has a name. It's like Wick's theorem or something like that. Anyway, this is true in a Gaussian theory. There's some numbers here. It's in Polchinski. Yeah. Okay. So this is true because theta is Gaussian. And now let's compute the two-point function of theta of x, theta of 0 at spatial separation. Theta is a massless, free massless field, which means that it decays like a power law. Okay? So what one is going to find is that you get that this is e to the minus 1 over x. Is this 1 over x? I think it's 1 over x. Does anyone exercise, compute the power in that? I think it's 1 over x. I'm seeing some nodding. I think it's 1 over x, yeah. Okay, let's go with that. Okay. All right. Which means x goes to infinity, this goes to constant. So as x goes to infinity, this thing goes away, and this goes to e to the minus 0, which is 1, which really means that it's a constant, because when I set O equal to e to the I theta of x, I was very cavalier with the overall size. Okay, so the value of this constant doesn't really make sense, but the fact that it is constant is coming from the structure of this. Okay, and therefore the symmetry is spontaneously broken. This is the honest way to do this. Okay, yeah, a really good question. Yeah, good. So this also goes to show that it's much easier to do calculations often in one duality frame than in the other duality frame. Okay, this calculation is wildly more complicated in this frame. Okay, it depends how much time. We have 15 minutes. So let me take some more questions. If there are no other questions, I can sketch why it's so much more complicated in this frame. But we'll take questions first. Any other questions? Yeah.
So here we are working in 3D Euclidean time.
Yeah.
There's nothing like Merlin-Wagner theorem.
Oh, no, there is Merlin-Wagner theorem. It just doesn't apply here. Okay. So let me, this is a great point. So let me just repeat that question for everyone. So there is something called the Coleman-Mermin-Wagner theorem, which says that you can only break symmetries in certain numbers of dimensions. Okay. In particular, for a continuous U1 symmetry, it is 3 non-compact dimensions or higher. Okay, this is I think what you were. Okay, I see your point. Yeah. So it doesn't. You could still worry about that, but it doesn't actually play a role here. Now it turns out. Let's just talk about where that comes from. Okay. So if you notice here, this calculation I just did depends crucially on the number of dimensions. Right. This number here is d minus 2. All right. In particular, if we had taken d to be equal to 2, what would have happened here? If we'd taken this to be d equal to 2, then we would have found, so in d equals to 2, it looks like you're getting 1 over x to the 0. X to the 0 is always log, okay? And what you actually find is that this goes like e to the minus some number times log x. That's what you would have found in d equals to 2 dimensions, okay? Which means actually that this goes like x to the, it goes like basically 1 over x to this number, okay? Notice as x goes to infinity, this now goes to 0, okay? And then there is no spontaneous symmetry breaking, okay? This result is what's called the Coleman-Mermin-Wagner theorem that says that you cannot have spontaneous breaking of a continuous symmetry in dimension d or in dimension 2 or lower, okay? This is, I think, the easiest way to see what's happening. This paper, yeah, I find this easier than Coleman's paper. Yeah. Okay. Does this make sense to everybody? What just happened? Yeah. Okay. Good. Okay. Excellent question. Yeah. So yeah, it doesn't apply because we're in 3 dimensions, not because of Euclidean time. If we did it in 2 Euclidean dimensions, this would have happened. You know, it's because we're in 3 Euclidean dimensions. Yeah. Yeah.
Probably saying yes because usually in quantum math you have, 3 means 2 plus 1, so. Euclidean dimensions.
Yeah. That's right. Then it depends whether you're doing it in the vacuum or at finite temperature. This is in the vacuum, but 2 plus 1 at finite temperature then is this case because yeah, that's right. Excellent. Good. Other questions? Yeah. Any other questions? Okay. Okay. So let's see. What shall I do? I could show you what the charged operators are under this. That's kind of interesting because it's super non-obvious, at least when I first thought about it. But is there any other question? Doesn't need to be about this. Any questions about the lectures in general? This is taking us a little bit of field, so I'm not sure. Any other questions? Yeah, let's see. Okay, I can do this, or okay. Let me explain maybe what these things are. So let's ask the following question. So over here, I just told you on this side of the duality frame that the charged operators were e to the I theta of x. Okay, these are charged, by which I mean they transform nicely under the symmetry. Okay? They transform like that. Okay. Okay. What is the charged operator here on this side? Okay. Now this is worrying, right? You're tempted to exponentiate a, but you just can't. I mean, it doesn't have the right number of indices, right? You can't exponentiate that. In fact, let's think back. We learned today that a good definition for the charged operator is that the charged operator is a place where the current is not quite conserved, right? That's a good operational definition for the charged operator. So what we're searching for is some object O, so that in the presence of the object O, we see a formula who looks like this. Right? This is a charged operator. Oh, thank you. We're looking for something that does this, okay? Okay, this is looking good, right? We're just gonna plug this into here and get some sort of useful formula. Okay, let's do that. So I plug this into here, and what do I have? Okay, I have epsilon mu nu rho d nu a rho O of y equals to this. Okay, and now I have 0. So O of y equals to something which is non-zero, here. This is 0 because, of course, by Bianchi identity, anti-symmetry, this is just 0. Okay, this is a terrible disaster, right? Okay, so what does this mean? What is happening here? What does this mean? So let me actually give everyone a second to just appreciate the magnitude of the disaster, right? I assume that there exists a field A in terms of which I can write down J. I then tried to find an operator so that this would be true. I computed its divergence, and I found the divergence is always 0 no matter what I do, and therefore it appears that I cannot create a local operator that is charged under it. Because any local operator charged under it must have a delta function contribution like this, okay? So I now have something which is 0 on the left-hand side times something which is non-zero on the right-hand side, okay? So does everyone appreciate the badness of this before I tell you the solution? Yeah, appreciates badness, good, okay. Okay, so I just told you a series of things that I did. Which of those was wrong? Anyone tell me? One of the statements I just told you was wrong. Which one was wrong? Anyone? Sorry? It's still local. It has to be local because it was local here. E to the I theta is a totally local operator, and all we're doing is rewriting things and playing some games. So if it was local there, it must still be local here. So that's not it, but it's something else. I lied to you very quickly, to be honest, you see, what I did was I said, I assumed there was a field A. Okay, I know that seems obviously true, right? We can always assume things exist. But in this case, it's a lie, all right? What I'm trying to do is construct something where basically the derivative of, let me write this in forms language. I'm trying to construct, if f equals to dA, I'm trying to construct this configuration where df is not equal to 0, okay? Which does happen. It's a magnetic monopole, right? So the point is, what we need is a magnetic monopole operator in A. That is what is charged under this, okay? Does that make sense to everybody? The lie was that I said A exists. When you have a magnetic monopole, A is not globally defined anymore, and so it doesn't actually exist. And this isn't a math technicality. It really just doesn't exist, okay? It's important, all right? because you get into meaningless things like this if you assume this. So let me tell you how to define this operator. Normally in life, when we define operators, we define them by saying that they are polynomials of fundamental fields in the Lagrangian. Okay? In particular, my Lagrangian has a field theta in it, e to the I theta, it's a good operator. Okay? There's another way to define operators, and it's as an instruction. So the charged operator is the following instruction. When you do the path integral over A, so if I want to put, so the instruction to put O of x at a point, you do the path integral over A. Did I call it capital, lowercase a? Yeah. Demand that integral of f over every S2 wrapping the point x equals to 2 pi. Okay? So this is a bit weird. This defines what's called a disorder operator. Okay? What it means is that, let's just think about what's happening operationally. I'm doing my path integral, okay? But I want to compute like, the presence of some operator O of x, okay? I am instructed by this instruction to pick a point x, and when I do my path integral, demand that for every S2, or rather, really it's for a small S2, so let me say small. For a small S2 wrapping this point x, I demand that the magnetic flux through that thing be equal to F. Okay? That's a demand. Right? That defines for you some sort of terrible local disturbance at the point x. In particular, the field A will cease to exist at the point x. Okay? But that's okay. I'm doing something violent there. I'm putting in, I'm sticking in an operator. And that violence that I'm doing, the fact that I'm forcing A to not exist, is the idea of placing a disorder operator at the point x. Okay? So this is what's happening. All right? And these things will play a role in the future lectures. In this particular case, I wasn't planning on discussing in this much detail, but this will play a role. Okay? Yeah?
Are you not now working with a different theory if you allow there to be an F which isn't dA? So, for instance, when you started with D,
yeah.
theta,
Yeah.
and then you wrote V as D theta, basically.
Yeah, that's right.
You had to impose this integrability condition that
Yeah, that's right. Absolutely. Yeah.
Why is it then valid? It seems like you should now impose that df equals 0.
Yeah, the correct way to do this, I have to remind myself, I believe the correct way to do this actually is if you want to, so you see, you could have tried to, here's something you could have done, right? You could have tried to do the duality while having an insertion of the operator e to the I theta in this thing and tried to see how does that work, right? That's another way to have played this game. And what you would have found is that the field V would cease to exist along lines connecting the thetas in just the right way to allow this thing to be possible. So I think what I'm really saying is the theory that I actually wanted was the one that allowed this. And here I was just somewhat quick because I was just being quick. But indeed, one can push on this. The theory that one wants is the one that includes the monopole bundles that are present here, because only then can you include the charged operators, and you want to include those charged operators. So yeah. Does that answer the question? No? Yeah. Good. Okay. So I'm basically out of time. So I'm going to leave you with one more thing. Okay, just because it's good to have something to think about. So we discussed just now sort of U1 QED. We discussed basically electrodynamics in 3 dimensions in quite a lot of detail, to be honest. We dualized it. We did all kinds of stuff. Monopoles are important. Now it turns out that if you formulate quantum electrodynamics on the lattice, okay, or if you obtain the 3-dimensional theory from a non-abelian gauge theory, then what happens is that both of those theories are actually confined, okay? U1 QED in 3 dimensions is generically in a confined phase, okay? And it turns out from the ingredients that I gave you, it's actually not hard to figure out why it's or maybe why is tricky, but it's not hard to write down a theory which has a confined behavior for this thing. So let me just tell you what your homework is, if you choose to do it. What we did was we took this operator e to the I theta, and the natural operator in the theta language, and mapped it to this language, and it was very weird, right? It's like introducing a monopole. Now there's a natural operator here, right, which is the Wilson line operator. Integrate A on some curve C. This is the natural operator on this side. And now my first question to you is, what is this object on the theta side? Okay, that's homework question number 1. And homework question number 2, once you understand that, is how do you mutilate this theory to make U1 QED be confined? And it's a simple mutilation, actually, in this language. It's very hard in that language. Okay, that's all I've got. Thank you all for listening, and yeah.